Welcome AP Physics, Electricity, and Magnetism students. Today's review topic is circuits. As is always the case in these review videos, I'm not going to go over everything in the circuits topic. The circuits topic, when we studied it, went on for several weeks. And so at this point, to go over every single thing in that topic, every kind of problem would just overwhelm you. It wouldn't really help you for the test. Remember, as I've said many times, you only need about 2/3 of the test correct on the AP test to get a 5 out of 5. So really what we should be doing while studying is looking at the main ideas only and the main kinds of problems. It's okay if we don't cover everything. One of the things I'm going to skip in this video is the derivations for the charge on a capacitor plate when it's charging and discharging. There'll be another review video. You could watch that if you want, but if you feel like you're overwhelmed, then go ahead and skip that, because again, that's not as likely to be on the AP as some of the things I'm going to be talking about today. So in the circuits topic, there are 3 ideas that are like the underpinning of the main idea, or one of the main ideas, which is Ohm's law. Current, resistance, and potential or voltage, more commonly referred to as voltage. First thing I want to talk about is current, and I want to remind you that current is a flow of electrons in a wire. And so you hook up a battery, the electrons in the wire start moving. They're able to move because the atoms of the conductor allow them to move, but we define the current as in the opposite direction as the flow of the negative charges. So in most problems, what you could do is you could pretend that current is a flow of positives going this way. Sometimes you'll be asked a question and then you'll have to contend with the fact that current is actually negatives flowing the opposite direction of I. Now, the symbol for current, as you can already see, is I. It's measured in amps, capital A, and the definition is dq dt. It's the rate at which charge is flowing. It's similar to velocity. Like you can imagine a sports car going down the highway racing has got a higher velocity than the little bicycle going down the street. So velocity is like the meters per second, how fast the meters are moving, or the object's moving in terms of meters. This is how fast the coulombs are moving, coulombs per second, which are renamed in amp. But more specifically, it's the derivative of charge with respect to time. But if you know the charge as a numerical value and the time as a numerical value, instead of the charge as a function, which we would need to use this expression, you could find the average current by taking the charge per time. So as an example, maybe 10 coulombs flows through a wire in 2 seconds. The average current is 10 over 2, or 5 amps. Okay? So there's more to current. Current charges, when they flow, they actually move randomly as they move to the right here. So they might be moving sideways at any time, backwards, forwards, but overall they have a drift velocity that way. So when we're talking about V in the current equations coming later, it's the drift velocity, kind of like the average velocity. You could think of it that way. The other big idea here is resistance. Now in most applications, everything has resistance, including metal wires. So the resistance is like, kind of, you could think of it as friction. It inhibits the flow of charge. There is an exception. Superconductors, you've probably heard about that earlier in science classes, not part of the curriculum. So there are some things with zero resistance, but everything else other than superconductors has resistance to it. The symbols are, the unit is ohms. When you see a squiggly line in a circuit like this, that means a resistor. So if you have a wire or any conductive material that has a certain cross-sectional area, like most wires are cylindrical, so when you cut them there's a circle on the end, pi r squared is the area. Now keep in mind, in this circuits topic, symbols are recycled. This is A is area, this A is amps. So just a little warning, you'll see that often. A lot of symbols get recycled. And then the wire has a certain length. The resistance of that wire is this rho symbol. It's like from the Greek alphabet. It's people call it P, but you just basically take a line up like that. That's called the resistivity times the length of the wire over the area. Longer wires have more resistance, as you could see from this formula, and thicker wires with a larger cross-sectional area have less resistance. This symbol, resistivity, is there because different metals, copper, gold, aluminum, they all, if you make them all the same size and shape, the different metals will all have different resistances. So this is the resistivity that depends on the particular conductor that you're dealing with. You look that up, or maybe you have to solve for it within this problem if everything else is given. But so more resistivity, more resistance, more length, more resistance, more area, thicker wire, less resistance. Also, and this is not, so I talked about recycled symbols. This is the symbol for charge density that we saw earlier in the Gauss's law unit. Well, not anymore. In this, it's resistivity. This was charge density over an area, sigma, not in this topic. This is the conductivity of a metal. So resistivity and conductivity are reciprocals of each other. The more conductive, the higher this is, the better conductor is, whereas the higher this is, the worse conductor it is. So this is a basic formula for resistance. Also, a concept that you need to know is that as the temperature of a conductor goes up, the resistance goes up. Temperature is not in this formula, so but that's also a concept that you need to know. All right, so this formula is not complete, is what I'm saying. Okay, potential or voltage, different symbols for that. V, delta V, emph, but the units are in volts. So again, look at this recycled symbol. This is voltage, the variable. This is volts, the unit, right? So it can get confused, a little confusing in circuits topic. So we're talking about batteries. You remember this from the unit. You have alternating small, big, plates like this. That indicates a battery. This end is the negative side. This is the positive side. I also want to point out that when you have a real battery, as opposed to an ideal battery, there's always a resistance that you can't get rid of because the battery is made of metal and other things, so there's always a resistance within the battery. We call that the internal resistance. Sometimes we give that the symbol lowercase r. And then we have the chemical reactions that are driving the electromotive force, pushing the charge out of the battery. So you cannot separate the two. A reminder, though, that voltage is the negative integral of electric field over a path. So voltage implies electric field. The battery here is creating an electric field in the wires, causing the charge to flow. If you convert this to just an algebraic expression, you could use this expression. If the electric field is constant over distance, you could say voltage is electric field times distance. And also this we learned earlier in an earlier unit, voltage is also, in addition to electric field times distance, it's the work per charge. So if you figure out the joules that you get out of an electron going through a chemical reaction and you divide by the charge on an electron, 1.6 times 10 minus 19, you would get the voltage of that particular device. Okay, so the current, resistance, potential, or voltage. All right, so let's move on to, as I said, one of the big ideas of Ohm's law, of the unit, Ohm's law. Okay, so here it is, I equals V over R. We studied this in class. More volts, more current, more resistance, less current. So it's basically very, very much common sense. We could represent this equation graphically like this. Voltage and current are proportional to each other. But sometimes we add a little portion of the graph here when the resistor starts to get hotter, and then we see what we call non-ideal behavior. This starts to taper off because the resistance goes up, so we're getting less current than we would expect if the resistance stayed constant. Another graph showing, expressing what the information in this formula, more resistance, less current, so we see more resistance, less current, less resistance, more current. Okay? All right. Another idea, so that's one of the main ideas relating these three ideas. Another big idea is current density. So density, we use the symbol J, and I put amps here, not A over meters squared, because again, the confusion, meters squared is area. The A per meter squared, I'm talking about the current per meter squared. That's the definition. It's how concentrated the current is. The smaller wire you force a certain amount of current to go into, the higher the density will be, because this is smaller. It's also the charge density times the drift speed or drift velocity of the charges. This is just a definition of what current density is. These expressions tell us what current density, what causes it. And what causes it is an electric field times conductivity is the current density. Now, interesting point. In the Gauss's law unit, in the conductor capacitor unit, I said that the electric field in a conductor was always zero. Well, I didn't say always. I said when the conductor's in static equilibrium. In every single electrical circuit, a flashlight, your wires in the walls of your house, when electricity is flowing, the electric field is not zero in the conductor because the battery maintains the electric field through the wires, and that's what keeps pushing the charges and keeps them moving. The continuously kept electric field caused by the battery. Okay, so that's what this is basically talking about. Another thing, power in a circuit. So when you turn a circuit on and you have a resistor and you're making current go through, the resistor heats up, or the light bulb, or whatever it is. So basically it's consuming energy at a certain rate. That's what we call power. So remember, power, the most basic formula in mechanics we learn is work per time. This is not watts. This is watts, by the way. So again, recycled symbols. Power is in watts. This is not watts, it's work. Work in joules per time. So what I'm going to do here is derive the expression for the power in a wire or an electrical circuit by realizing from this formula, if I solve for work, I get QV. So I'll put QV in for work right here. And then I'm going to separate the Q and the time together. And Q over T is the current, as we saw over here. And so what I have is current times voltage. That derivation is in the curriculum, by the way. You have to be able to do that. That's what they expect you. They expect you to possibly do that. We could derive other forms by just replacing either I with V over R. So we have V over R times V, giving us V squared over R. Or V equals IR. All these are coming from Ohm's law, by the way. V equals IR, so I put IR in for V, and I get I times IR, or I squared R. So, different forms of power in a circuit. All right, let's move on. Okay. So, now, you could have a simple circuit with just a battery, a resistor, and wires, but you could also have more complicated circuits. The simplest, more complicated circuits you could have is something called series, something called parallel. When the resistors are in series, they're all in a chain. When they're in parallel, they connect both sides to the battery. Now remember, all throughout the year, I've been saying that voltage is always two prongs when you plug something in, right? Every outlet, you need at least two wires going in for the appliance to work. Because voltage was electric field times distance, so we have a path over which it moves one prong to another. So the voltage of this battery doesn't go to R1. The voltage of the battery goes, one prong of it goes right here, and the other prong goes right here. So the voltage gets split to all the resistors. Here the voltage goes, both sides go to every single resistor. And that's the key. That's what makes a series versus a parallel circuit, is how the two sides of the voltage are applied to the circuit elements. It doesn't mean anything about the way that you lay them out. Like I could move a resistor down here and you'd say, oh, those are parallel. No, they're still in series, okay? So, basic ideas, you know these. To get the equivalent resistance of all these, you just add up all the individual resistors. The current coming out of the battery, there are no turns that it can take, any detours, so whatever amperage is coming out of the battery goes through all the resistors equally. That's what this is saying. And the voltage gets split up, right? Two prongs to the voltage. One side is here, one is there. So if this is a 12-volt battery, here are the two sides of 12 volts. So maybe they all get 3, 3, and 4, 4, and 4, and that gives us 12. Or they could split it unequally. That's what this is saying. The total is split up among the individual resistors. Whereas in parallel, the equivalent resistance is with the reciprocal rule. The current basically splits up. Say I have 10 amps coming here. Maybe I have 3, 3, and 4. So that's what this is saying. The current coming out of the battery splits into all the individual resistors. And the voltage, whatever voltage the battery is, all the resistors get that same voltage. So if this is a 12-volt battery, 12 volts. 12 volts. 12 volts to all of them. That's what that expression is saying. A fancier way to say what I said here is with what we call Kirchhoff's rules. There are two of them. There's what we call the junction rule and the loop rule. The junction is when a junction is whenever you have multiple wires that join together. Okay, so take a bunch of wires, twist them together. Where the wires are twisted together is a junction, a meeting point. Whatever current comes into that junction has to be equal to whatever current is coming out. That's basically this expression right here. See, this, whatever current's coming into the junction, which are basically these three resistors joined together, has to be the current coming out to the three resistors. This is I in, this is I out. So this is just a fancier way to state this rule right here. The loop rule says that in any given circuit, the sum of the voltages has to be 0 when you tally the voltages going around a circuit. That's basically this expression right here. If I mark this as a starting point, remember I said with Kirchhoff's junction rule at the time, I said imagine you're a little ant with a little tiny voltmeter walking around this circuit, measuring all the voltages and adding them up. The sum in the end is 0. So the little ant goes plus whatever the voltage of the battery is, then goes through each resistor measuring IR, but in the downstream direction. If it's going, the ant is walking with the current, then it's going to lower voltage, just like water flows downhill. So minus IR, minus IR, minus IR. Plus V, minus V, minus V, minus V. Or you could move all the negative V's to the other side and get this expression right there. All right, now there are a lot of Kirchhoff junctions problems, or Kirchhoff rule problems, some involving system of equations. I'm going to skip those problems today, again, because I don't think they're very likely to be on the AP. But I'll show you something else that is more likely or more possible in terms of it being on the AP with Kirchhoff's rules. And that's finding the terminal voltage of batteries. We say a battery has a voltage of 1.5 volts or 12 volts or something like that. But the truth is that's only when no current's going through the battery. Once you hook it to the circuit, the voltage will start dropping. Not because the battery's going dead, but because there's current in the battery. And so there's this thing called terminal voltage of batteries. And that's because there's an internal resistance within the battery. So what I have here is a simple circuit. I have a 12-volt battery, and this is the internal resistance of 1 ohm. Remember, all real batteries have that. And this is a 4-volt battery, battery EMF-B versus EMF-A. And notice they're like fighting each other. One wants current to go, this one wants it to go in a clockwise direction, this one's trying to make it go in a counterclockwise direction. And this also has an internal resistance. Obviously, the higher volts is going to win out, and the current's going to go like this in the clockwise direction. Okay? The first thing I could do is I could find the current using Kirchhoff's loop rule. 0 is the sum of the voltages. So again, I pretend I'm a little ant starting at point A. And I'm going to tally up all the voltages that I encounter as I walk in the direction of the current, right? I'm going to follow the current and measure all the voltages. So the first thing I encounter is this resistor of 1 ohm. And so the voltage I'd measure is negative IR. I don't know what I is, but whatever it is, IR is the voltage I'm going to step through in the downward direction with the current, so minus IR. Then I get to the chemical reactions of the battery, the EMF. I go from the negative terminal to the positive, so I got up 12 volts. Then the ant continues walking, hits this resistor, walks through it and measures minus, because it's going downstream, minus IR. And then the ant gets to this, the positive side of the chemical reactions within this battery, and then it walks to the negative side, so it goes down 4 volts instead of up 12 volts through this one. And then encounters the resistor in the direction of current, minus IR, completed the loop. So all these voltages tally have to be zero. That's Kirchhoff's loop rule. There's only one unknown here. I could solve and get 1 amp. Now, the next thing I want to do is find the terminal voltage of this battery, which is the voltage from point A to point B. So now it's like the little ant walking, but starting at A and stopping at B, not going all the way around. What's the voltage between A and B, the two terminals of the battery? Well, the ant first walks through the internal resistance inside the battery. Minus IR is the voltage it passes through when it walks through there. Then it gets to the chemical reactions and it goes from the negative side to the positive, so we have plus 12 volts. Okay? So when we evaluate that, we get plus 11 volts. We only get 11 volts even though it's a 12-volt battery, right? We say that in quotes. At this point, with this particular circuit, it's only outputting 11 volts. That's what we call the terminal voltage of the battery. Whenever any battery is discharging, the voltage will be less than what it is when it's just sitting and you measure the voltage without any current in it. Battery here, battery B, we could figure out its terminal voltage by finding the voltage with our little ant walking from C to D, from one terminal of the battery to the other, and tallying up the voltages it encounters. Delta V C to D, well, first thing the ant encounters here is that resistor. So the voltage to that resistor, now, the current's going down, right? So when the ant walks this way, it's not going minus IR, it's going plus. It's going upstream of the current. So, plus IR, not minus IR. We're going against the current. Plus IR, we're going to a higher voltage here. And then the ant gets from the negative part of the chemical reactions to the positive, so it goes up the 4 volts. It goes up through the resistor, up through the chemical reactions, we get 5 volts. Remember, it's only a 4-volt battery. But when it's charging, because that's what's happening, we're forcing current in backwards, we're recharging the battery, the terminal voltage is higher than the voltage of the chemical reactions during the charging process. Okay, so voltage of the battery is not always equal to the EMF. Another couple things, the rate at which the chemical energy is being increased in this battery, remember, rate of energy is power. Power is work over time, right? The joules per second, that's the rate of chemical energy going in. Well, I have 1 amp, well, first of all, it's IV from the previous page. The current's 1 amp, and I'm forcing it through the chemical reactions, which are 4 volts. So the battery is gaining energy, chemical energy, at 4 watts. But the battery is gaining even more energy than 4 watts, more at a faster rate than 4 watts, because the terminal voltage of the battery is 5 volts, and we're forcing 1 amp through the 5 volts here. And so the battery is actually absorbing not 4 watts rate of energy, but 5 watts. That includes the heat. The chemical reactions are 4 watts increasing at that rate, and the heat in that resistor is increasing at 1 watt, making a total of 5 watts. So that's an example that something that's more likely to be on the test regarding Kirchhoff's rules. All right, let's move on. So next topic. I gotta move it just down, move this a little bit. Okay. right, so combination circuits. Now, very often we don't have circuits that are just series or just parallel. We have circuits that have some parts in parallel, some parts in series, so on and so forth. This is showing you the basic strategy of solving and simplifying these problems and solving for different things they might ask. So what I have here is a 12-volt battery, 6 ohm, and then over here 3, a 4, and a 6 ohm in this arrangement. And what I want to do is calculate first the total current coming out of the battery and then the current only in the 4 ohm. So what I first have to do is simplify this circuit and try and get it down to just one resistor. So I know the resistance the battery feels of all of these. All of these together act as one equivalent resistance. That's what I'm looking for. So what I do is I look in the circuit and find parts of the circuit that are either purely series or purely parallel. For example, these two are not in parallel. Some people say, well, I'll start here. These two are in parallel. No, in order for them to be in parallel, both the front ends of the resistors and the back ends have to be directly connected. They are not. These are all in the way. Some people might say, well, the 3 and the 4 are in series. They are not. In order for something to be in series, two resistors, all the current passing through the first resistor has to pass through the second one. But look here, we've got some of it that can escape on this branch. So they don't have the same current, they're not in series. The only part of the circuit that's purely series or purely parallel is what I started here circled in green, the 4 ohm and the 6 ohm. I could find the equivalent resistance of those using the parallel resistor rule. If I did my math right, it's 3 ohms. So what I do is I start there and then I redraw the circuit again, replacing those two with the equivalent of 3 ohms. So I simplified it. And I keep simplifying in this manner until I get down to one resistor, one battery, and then I can solve for the current. So now I look what's series, what's parallel here. Again, you might say, well, aren't these in parallel? Right? No, again, the front ends are connected, but not the back. There's a resistor in the way. The only part that's purely series or purely parallel are these two in series. So I could use the series resistor rule, get 6 ohms, and redraw the circuit like this. Now these two are finally in parallel. I use the parallel resistor rule and I get 3 ohms. So back to this original diagram, all of the resistors in that circuit collectively act as one 3 ohm resistor. So I could find the current out of the battery by using total volts over total resistance, and I get 4 amps. That's what's coming out of the battery into this complicated circuit. Now, the other thing that I want to calculate is the current in the 4 ohm. That's right here. So now what we do if we want to find a current of a piece is we got to work our way backwards. And notice, you may have noticed I labeled some of these points A, B, A, B, A, C. And I do that to help me analyze and figure out what parts of the things about different parts of the circuit that allow me to find the current in this 4 ohm. So the first thing that I'm going to do is find the voltage between A and C. And I could do that from Ohm's law. The current from A to C. I could do that from Ohm's law. I know that it's this 6 ohm right here has the full 12 volts of the battery because it's in parallel in the circuit. So the current down this branch is the voltage of this branch, 12 ohms, and the resistance of this branch, which is 6 ohms, 2 amps is going between C and C and A. Now I can find the voltage between A and B right here. How do I do that? Well, I use Ohm's law again, V equals IR. There's 2 amps and 3 ohms between A and B, right? 2 amps here, there's 2 amps here. So IR, 6 volts from here to here. Now, finally, A and B are right here, so I know that I have 6 volts from here to here. I have 6 from there to there, which is the voltage of the 4 ohm. So finally, I could do I equals V over R. There's 6 volts here and 4 ohms here. So I put that into Ohm's law, and I get 1.5 amps. So that's an example of how you analyze combination circuits. Okay, moving on. RC circuits, resistor capacitor circuits. So one of the things you have to be able to do is derive these formulas, okay? I'm not showing all the details again, okay? I'm going to show you the highlights, and then I'll show you the details in the next video if you're interested in watching. So here's a circuit. If I'm creating a simple voltage source and a resistor and capacitor and a switch, and when the switch flips down, the capacitor will start charging. It's initially uncharged. I also added an ammeter and a voltmeter into the circuit because that's also something in the curriculum that you have to know how to hook in ammeters and voltmeters in the circuit. An ammeter always goes in series in the circuit within the loop. It's like a toll booth. So if you want to measure the amount of cars going through a highway, you don't put a toll booth to the side. All the cars would pass through and never go through the toll booth. You have to put it within the loop, okay? So it's inside. The voltmeter, though, always goes in parallel, not in series like the ammeter, but in parallel with the element you're measuring the voltage of. So this would measure the voltage correctly for the capacitor. So just a little aside. But how do you derive the equations? First thing, as I'm going to talk about in the video in more detail, there are 4 steps to solving these equations or deriving them. The first one is you have to make a differential equation. In mechanics, we use Newton's laws, A equals F net over M, to make a differential equation in those problems. What we do instead here is we use Kirchhoff's loop rule. Sum of the voltages around the path is 0. So I labeled this A. Again, I get my little ant out, have him walk around in the direction of current, and tally up all the voltages that the ant encounters. First thing, the ant walks from the negative terminal to the positive terminal of the battery, so it goes up plus EMF. Then the ant keeps walking, hits the resistor, the current's flowing this way, right? So it's going downstream through the resistor, so it's going down voltage. How many volts? Ohm's law, V equals IR. IR. Sometimes they use lowercase I, as you probably remember, for current. Capital I, lowercase I. You see them both in the topic. The ant keeps walking and then walks from this plate of the capacitor to this one. Now as the capacitor is charging, this side's positive from the battery in the direction of the current flow, and this side's negative. So the ant goes down negative volts again, and it goes Q over C. That you get from this basic capacitor equation, C equals Q over V. If you solve that for V, put the V over this side, divide by C, you get Q over C. So this is still not a differential equation. A differential equation has a derivative in it. The way you get a derivative in there to make this a differential equation is you replace I with dq dt, the definition of current. So here's my differential equation. So step 1, make a differential equation using Kirchhoff's loop rule. I skip step 2, 3, and 4, and I just put the answer. Because, again, most of the time on the AP when I see these come up, most of the credit is actually setting up the differential equation. Sometimes this is 3 points, and this is when you get to here and solve, you get 1 point. So this is the important part, being able to use the loop rule in terms of getting points on the AP test, in my opinion. So the other steps are make a differential equation using Kirchhoff's loop rule. Then you separate the variables and then you integrate both sides, and then you solve for Q. Separating the variables means you get all the Q's on one side, all the times on the other. So those are the 4 steps I'll mention in the next. I'll go through those in the next video. Here's the charging equation for charge on a capacitor. C times EMF is the final charge. This 1 minus exponential e to the negative t over RC is this rising function. It rises to C times EMF as time goes to infinity. Okay? Sometimes this RC in the denominator of the exponential is redefined as the time constant, tau. This is the same symbol that we used in mechanics for torque. Okay? So sometimes it's e to the negative t over tau. Okay? So don't be alarmed when you see that. Tau is just RC. The charge rises, so does the voltage on the capacitor. It starts at 0 and eventually becomes the voltage of the battery. So you could basically just turn this into a voltage equation, 1 minus exponential. and I use the tau. To find the current, what you would do is take the derivative of this with respect to time, and you'd get the current right there, Mth over R. I'll show that in the next video. It decays exponentially to 0. Discharging the capacitor. Now we have the capacitor charged up, and you have a switch here waiting to discharge it. When the switch flips down, the charge will come off the plates and go in this direction, go through the capacitor, until through the resistor until the capacitor gets to 0 charge. You have to be able to derive these also. You follow the same 4 steps. You make a differential equation using Kirchhoff's loop rule. So again, we put a little dot for our starting point, and we imagine that we're a little ant walking around, tallying up the voltages that we measure with a little tiny voltmeter around a loop. When we do all that tallying up, we get 0 for an answer. So the first thing the ant walks through is it walks through the capacitor starting at the negative plate and going to the positive plate. So it goes positive up a certain amount of voltage, and that's Q over C, as I mentioned from here. So it goes up the voltage, then keeps walking and goes downstream through the resistor, minus the voltage of the resistor, minus IR, and then it completes the loop. And so there's our Kirchhoff's loop rule. Tallying up the voltage, we get 0. Still not a differential equation. So we got to replace I with the derivative dq dt. But notice there's a little extra minus sign over here. Why is that minus sign there? The reason why is because the capacitor is actually going down in charge. dq dt is technically negative. So if I don't have that negative there, I'm plugging in a negative current. And I just want to plug in what the current is as a positive quantity. So I have to put that little minus sign in there to negate or make the current, which is the dq dt negative, make it the current positive. So that's step 1. I made a differential equation using Kirchhoff's loop rule. What I have to do next is separate the variables, get all the q's on one side, all the t's on the other, integrate both sides, and solve for q final. And that's what you would get here. The charge just exponentially decays e to the minus t on RC. And then you take the derivative of this and you get the current as a function of time, and the current decays e to the minus t on RC. So both the charge and the current decay. A way to remember these is just remember the e to the minus t on RC is in all the formulas. Discharging, the charge obviously decays, and so does the current. Charging, the current decays also. So it's just original times the exponential in all cases. The only exception is when the capacitor is charging. Then the charge doesn't go to 0. It starts from 0 and goes up. And the way you achieve that with an exponential is you have the 1 minus exponential. So RC circuits, a lot of times you're just applying these equations by plugging in all the terms and solving for an unknown, like maybe the time, when is the charge a certain value or something like that. All right, let's move on. Okay, so sometimes we have multiple capacitors in a circuit, capacitor-only circuits. So we can have series and parallel capacitor circuits. And so you see the pictures. I don't need to explain those again. And the thing that changes, the voltage expressions are the same. The voltage gets split up, and here they all get the complete voltage. So this is the same as for resistors. The current equations become charge equations. Whatever charge comes out of the battery and eventually reaches equilibrium, every capacitor has the same amount of charge. Whereas in parallel, whatever charge is stored in these capacitors, you add those charges up to get the total charge that came out of the battery. The equivalent resistance rules are switched. This is the parallel resistor rule. It applies to series capacitors. This is the series resistor rule. It applies to parallel capacitors. Okay, so just keep that in mind. So, this is just basic application. Okay, the last thing for today, capacitors in combination circuits. So sometimes we have complicated circuits with resistors and capacitors all within, nothing's purely series or parallel. There's parts that are in parallel, parts that are in series. So this is the original circuit. And what we do in problems like this is we usually analyze them only for what's happening at the beginning moment when the first switch flips down. The problem will say initially. What that means is time is 0. The timer our experiment has just started when that switch flips down. And then you also analyze it, quote, after a long time. What that means is time has gone to infinity, approached infinity, and the capacitor is charged up. Time infinity after a long time could actually be, as I mentioned in class, less than a millionth of a second. What we're talking about is a long time on the time scale of the capacitor. So it basically reaches its final state. Alright, so initially when this switch flips down, the capacitor, with having no charge, has no resistance to the flow of wire, through the flow of current through it. So it basically just acts like a wire. So the current, when it passes through resistor 1, it will bypass resistor 2, and in that initial moment, all the current will go through the capacitor as a wire. So R2 is completely bypassed. So to the battery, the current is just inhibited by only that resistor because it can freely pass through the capacitor. That's only at time equals 0, M over R1. That's how the circuit behaves. After a long time, when the capacitor fills though, it basically becomes a blockage. So no more current can go this way because the capacitor is full. So all the current will now switch and go down this direction through R2. So this is how the circuit behaves. It's as if the capacitor isn't even there. And so the current final is just M over the equivalent resistance, which is R1 plus R2. Another point, the voltage of the capacitor. A lot of students will say, well, that's a 12-volt battery, so after a long time, the capacitor is just filled with the 12 volts. Not true. The voltage of the capacitor is the voltage of this resistor because it's in parallel with that resistor. So whatever volts this resistor has, if this is 12, maybe this only has 4. So then this is 4 volts. Okay, not the... And another thing, I could graph the current as a function of time. It would start off at this value and exponentially decay to this value. So you don't have to come up with equations like we had in the previous part with just a simple RC circuit. All you're responsible for is what happens in the beginning, what happens after a long time with circuits like this. So those are the highlights of the circuits topic. Hopefully you have all the notes down, look through, read through them a couple times, and then go ahead and try some of the circuit problems. And if, like I said, if you want to watch the next video, which is how to derive the current as a function of time for capacitor resistor circuits, you're welcome to, or you're welcome to skip it. All right, I'll see you in the next review video.